Hello friends, welcome back to You Can Do TV. One of the largest excavator ever built weighed 13,500 tons and moved on 131-foot shoes. Yes, shoes. Some of these machines don't crawl, they don't roll, they step. And even at that scale, one belt jam a mile away can freeze the whole operation. We're breaking down how giants like this are built, moved, and kept alive. Wait until you see one of the largest walking machines humans have ever built. Somewhere in Western Germany, a machine roughly the length of the Titanic is quietly working its way through open earth. It weighs around 14,200 tons, stands 315 feet tall, and rides on 12 crawler tracks. The rotating wheel at the front is almost 70 feet across, with 18 buckets swinging around it. Each bucket alone can hold a small car. The wheel turns slowly, almost patiently. Look away for a minute. The hillside is smaller. Every rotation strips off enough material to fill dozens of dump trucks. The whole operation runs on a crew of about 5 people. Here's a detail almost no one mentions. The biggest excavators on the planet have never been through a factory door. They can't fit. A shovel like this weighs around 660,000 pounds when finished. No truck, no rail car, no ship delivers that in one piece. So the mine becomes the assembly line. Trucks roll in with modules, cranes work through the day, and a mountain eater takes shape from the desert. Now watch what a month of assembly actually looks like on the ground. A convoy of trucks rumbles across the African bush toward a platinum mine. Inside those trailers are the pieces of a 500-ton hydraulic excavator, broken down into modules just barely small enough to move on public roads. A flat pad about 40 by 70 meters gets cleared at the mine. That is the workshop. Everything happens under open sky, in wind, in heat, in dust. The first piece to go down is the slew ring. The giant bearing the entire upper machine will rotate on. Surfaces are cleaned, adhesive applied, then a 120-ton crane lowers the ring onto the undercarriage. Bolts go in by hand first, then get torqued down with hydraulic wrenches. Miss the torque spec on one bolt and the mine crew hears about it later. Years later, from a maintenance report, track carriers arrive next, each swung into position with millimeter precision. Track pads follow, each one weighing almost a ton. A bulldozer helps drag the links into place. Guess, a bulldozer running errands. Next comes the superstructure. 2 100-ton cranes work together, taking directions from one marshaller on the ground. The frame lands on the slew ring, guided by a dowel pin. Then the 37-ton motor module, then a laser alignment step that tolerates errors no bigger than 1/100 of a millimeter. They haven't dug anything yet, and the machine is already aligned tighter than most Swiss watches. The boom lifts next, around 50 tons in one piece. Cab, cooler, walkways, railings, all bolted on. Last is the 60-ton counterweight, lowered so slowly you could set a coffee cup on it and lose interest before it landed. Then, hydraulic and electric lines get run. Days of work in cables alone. Rope shovels get built the same way. Outside, module by module, under a couple of very tall cranes. The house arrives first, a huge black box holding the electric motors, cable drums, and control gear. It gets welded and bolted onto the crawler frame. Then the boom goes up, a straight steel arm long enough to reach several stories into the air. Then, the dipper handle. Then, the dipper itself, a bucket wide enough to hold a pickup truck with room around it. It takes weeks, and once running, the shovel will not leave that mine for the next 20 to 30 years. It arrived on 40 trucks. When it eventually leaves, it'll be in about 2 loads, and only after it's been cut up. For context, here's how a normal-size excavator gets built. Steel plates are laser cut, robots weld, paint bakes on in ovens, cabs drop onto chassis on a moving line. It rolls off the factory floor complete, drives onto a trailer, and gets delivered. The giants at the top of this video will never see any of that. They're too heavy for roads, too tall for tunnels, too wide for bridges. There's another reason mine assembly works. The logic of taking a hydraulic excavator apart or putting one together holds at every scale. Watch a smaller machine getting fully restored in a workshop, and you see the same sequence that unfolds out in the desert, just compressed. The old machine rolls in tired, hoses cracked, paint faded, hydraulics leaking. Workers start at the top and move down. The boom comes off first, pins pulled with a press, then the stick, then the bucket linkage. The upper house gets lifted by a crane, exposing the swing bearing underneath. Down at the base, the tracks come apart pad by pad, each one heavy enough to need a forklift on its own. The engine gets pulled and rebuilt. Hydraulic pumps come off, get opened, checked for wear on the swash plates, and reassembled with fresh seals. Then everything runs in reverse. Slew bearing goes down first. Upper structure lands on it. Boom pins get driven in with a wheel loader, nudging the pin home. You already saw a wheel loader driving pins on the giant machine earlier. That wasn't improvisation, that's how it's done. Fresh paint goes on last, the machine gets its bucket back, and it walks out of the shop looking almost new. Now take that logic and scale it up 20 times, then move it 500 miles from the nearest paved road. That's a rope shovel assembly. So what happens once these things finally start digging? Here's the part that surprises almost every first-time viewer. A giant excavator can't really work without the mine around it agreeing to keep up. Watch what a bucket wheel excavator actually does. The wheel at the front rotates continuously. Each bucket digs, lifts, and dumps its load onto an internal conveyor within a few seconds. That conveyor feeds a longer boom conveyor. The boom conveyor drops the material onto a network of belt conveyors running across the pit, sometimes for several kilometers, all the way to a stockpile or a processing plant. If any one of those belts stops, the excavator stops. Everything stops. The wheel keeps spinning for another few seconds out of momentum. Then the operator hits pause. A machine that took 5 years to build, sitting still because of a belt jam a mile away. That's the trade-off of continuous mining. Speed depends entirely on the flow behind you. At a much smaller scale, this trencher shows the same problem in miniature. A rotating wheel of buckets cuts a narrow trench for pipelines or cables at high speed in soft to medium soils. It looks like a mini bucket wheel excavator, and mechanically it is one. The spoil comes off the wheel, gets thrown out to the side by a chute, and lands in a clean windrow, ready to be pushed back later. Take that windrow away and the whole thing chokes on its own dirt. The problem doesn't shrink with the machine, it just gets easier to see. Not every giant excavator uses a wheel. Some use a chain. This is the final walk of a bucket chain excavator, captured in time-lapse as it steps out of an open-pit lignite mine in the Czech Republic after finishing 34 years of digging. The machine weighs 5,600 tons and stands 40 meters tall. Peak power draw hits 9,000 kilowatts. Its hydraulic walking system holds 15,000 liters of oil just to lift the machine one step at a time. 6 operators run the whole thing across snow and mud. It is not winning any races. So why choose a chain over a wheel? The chain digs down and toward the machine, not out and away. That geometry lets it cut a clean vertical face below its own level, which a wheel struggles with. It also handles sticky or wet material better because the buckets scrape rather than fling. The trade-off is speed. A chain cycle's slower than a spinning wheel of similar size. You give up some tons per hour, and in exchange the machine can actually reach the material you're after. And when you push chain design to its limit, this is what you get. The K-10,000 hits 10,000 cubic meters per hour of theoretical output. It reaches 70 meters horizontally from its own center line, cuts 35 meters high and 4 meters below its base, and swings a full 360 degrees. Operating weight sits at 6,000 tons. It walks on shoes very, very slowly. To see why both designs exist, side by side, drop down in scale. This is the smallest bucket wheel excavator in the family, only 74 tons of operating weight. Bucket volume is around 100 liters. Theoretical output, 500 cubic meters per hour. Compact enough to be trucked to a site as a whole machine. Look at how it moves material. The wheel spins, each bucket scoops, tips its load onto an internal belt, and passes it along a wheel boom to a longer loading boom. The loading boom hands off to a conveyor line, fast, continuous, low resistance. Perfect for soft, dry material like brown coal or overburden. Put that side by side with a chain machine and the choice clicks. Wheel for soft and dry, chain for stiff and sticky. And this is only half the family, because somewhere out there, another giant is about to take a step forward. Literally. But sometimes even walking isn't enough. Sometimes the dragline has to travel farther than its own shoes can carry it. So the crew brings in something almost as absurd as the machine itself. A 2,000-ton dragline gets loaded onto a multi-axle heavy-hull trailer with dozens of tires spreading the weight across the ground. Movement is slow, measured in feet per minute. Pickup trucks lead the way. Dust hangs in the air. The trailer alone would look massive without the dragline on top of it. So what happens when there is no ground at all? When the surface under the machine is water or half water and half mud? You build the machine to float. This 360-ton pontoon excavator was assembled in Hamburg for a container terminal project on the North Sea coast. It is a full-size hydraulic excavator sitting on top of a barge, and getting the two to work together takes serious engineering. The heart of the assembly is a 7.7-meter elastic suspension ring bolted between the pontoon and the excavator's slew bearing. That ring keeps the machine from tearing itself apart every time the water moves. Tides in Hamburg's harbor rise and fall constantly. Crews had to readjust component positions during assembly because the pontoon itself was shifting under them. Once operational, the machine ran on 3 shifts, 24 hours a day. Job: dredge mud and sand from 15 meters below sea level. Over 265,000 cubic meters in 6 weeks. Bucket cycle, 45 seconds. Loading rate, 1,000 cubic meters per hour. A machine that big, working from water that shallow, moving that much dirt without ever touching the seabed with a track. That is the trick. Pontoons only solve half the problem. What about the ground that isn't quite water and isn't quite land? Enter the Amphibious excavator. Instead of tracks, this machine sits on 2 hollow pontoon shoes with cleats bolted to the outside. Those pontoons float when the water gets deep and grip when it doesn't. Watch one work under a bridge in a muddy channel. It clears vegetation, dredges silt, and pulls itself up a bank without needing solid footing anywhere. Here's how you actually build one of these things. 2 large gray pontoon shoes get lined up on a flat pad. Cross beams tie them together. Then a standard hydraulic excavator, upper structure and all, gets craned into position on top and bolted down. That's it. The excavator that was designed for dry ground is now a boat, and it didn't need a redesign to get there. Once assembled, the machine gets trailered to the water at night, launched onto a demonstration pond, and given its first task. Scoop mud without tipping over. The first minute in the water is the most nervous minute anyone on that crew will have all year. After that, it's routine. And you don't need a special excavator to get amphibious capability. These pontoon undercarriages come in sizes to match 8-ton, 14-ton, and 20-ton excavators, and any brand of upper structure will bolt on. Side pontoons and spud piles get added for extra float and stability when the water gets deeper than the shoes can handle. Same idea, different combination. A 20-ton class Japanese excavator upper structure sits on a purpose-built pontoon undercarriage, and now it can wade through swamps, ponds, and river shallows that would have swallowed the original tracks in about 4 seconds. And once the machine is free from the ground, engineers start playing with something even weirder. Not floating, reaching. Not every excavator problem is solved by adding more power. Some are solved by adding more reach. This is a 270-ton long-reach excavator, carrying a 3-part boom stretching 42 meters end-to-end. Its job on this project: trim slopes and place armor rock on seawall reclamations. You cannot walk out there. The excavator can, from about 130 feet back. Then there's the opposite problem. Sometimes the space is too tight, not too far. This tunnel excavator solves it by shrinking upward and folding inward. Operating weight is around 45 tons. The engine puts out 150 kilowatts, with an optional 190 kilowatt version for harder rock. That's roughly 200 to 258 horsepower, going into a machine that has to fit inside a tunnel between 5 and 8 meters tall. Watch the shape. The upper structure is compressed vertically. The counterweight is thinner than a normal excavator's. The boom articulates in a way that lets the machine work close to the tunnel wall without smashing into the ceiling. Cab is low. Cameras replace direct sight lines in the tightest spots, and dust extraction is built into the platform because operating a diesel engine inside a tunnel is a serious ventilation problem. Regular excavators don't fit in tunnels. Tunnels don't compromise on shape. So this excavator did. Every inch of the upper structure was redesigned to accept the ceiling above it and the walls beside it. The bucket still digs at full force. The rest of the machine just apologizes politely for existing in a smaller box. And sometimes the reach problem isn't sideways. It's downward, sideways, and diagonal all at once. This mobile walking excavator solves geometry using its legs, not its arm. 4 independently articulated outriggers with wheels on the ends lift the entire chassis off the ground and reposition it across broken terrain, cliff edges, and stream beds. Watch one demonstrate. The machine crouches, extends 2 outriggers, plants them, then walks the other 2 forward. Each leg carries part of the weight. It looks awkward. Each leg carries part of the weight. It looks awkward. It gets to places a normal excavator can't even see, let alone reach. Same problem as long reach. Different answer. On a smaller scale, this is what reach where humans can't. Looks like day to day. A standard excavator pulls a gum tree out of an irrigation lateral by the roots. Try that with a chainsaw and a shovel. You'll be there next week. These machines cannot afford a day off. Every idle hour on a rope shovel costs the mine thousands in lost production and delayed truck cycles. So the crew builds maintenance into the operation itself. Watch a big electric rope shovel working an iron ore mine. The shovel loads a haul truck in about 3 to 4 passes. Truck pulls away, empty truck moves in. Cycle repeats every 30 to 45 seconds. Between shifts, greasers walk the machine with pump lines checking pins, bushings, and cables. Between weeks, ropes get inspected for broken wire strands. Between months, a full crew climbs into the house to swap wear plates and check the swing gear. The shovel never really stops. It just gets checked while it's still warm. And when something big does wear out, replacing it is a project of its own. This is a dragline propel gear, the massive tooth component that lets the machine step forward on its shoes. Manufacturing one from raw steel takes weeks. Circular billets get welded up into blanks. Blanks go onto a vertical turning lathe for the initial shaping, where cutters throw off metal shavings the size of your hand. Then the gear moves to a hobbing machine 8 meters across, where each tooth is cut into the ring with millimeter precision. The final finished gear is bigger than most delivery vans, and it's a spare part. One of them, sitting in a mine yard, waiting for the day the current one finally gives out. Older draglines get upgraded rather than replaced. New motor controls, new payload monitoring, new operator screens showing bucket weight in real time. The display in the cab reads out shift averages and target loads for every dig, so the operator knows immediately when a bucket is coming up light. When the base of the dragline itself needs work, the mine pulls off something almost unbelievable. The upper structure gets separated from its circular tub, and the tub gets dragged out from underneath using a line of scrapers pulling in unison. Aerial view shows dozens of pieces of yellow iron working together to move a circular steel foundation the size of a small building. All this so a bearing underneath can be replaced. And the bucket, when it comes off, gets flipped by a forklift in a cloud of dust. And here comes the next generation. Bigger, smarter, and still not able to work alone. This is one of the largest hydraulic excavators built in China, weighing roughly 700 tons. Cab is fully digital, with screens replacing the analog gauges that used to line the operator's console. Payload monitoring runs in real time. Fault codes get transmitted to a maintenance office before the operator even feels the problem. Watch it load a haul truck. 3 passes, maybe 4. Truck rolls away, next truck pulls in. Cycle repeats. All the technology in that cab is impressive. The machine still stops the second the truck line breaks. No amount of digital telemetry solves that. If the trucks don't arrive on schedule, the excavator sits. If the crusher downstream is backed up, the trucks stop, and the excavator sits with them. The whole mine breathes as one system. The machine at the front is just the loudest part. And the operator inside all of this is running the machine with fewer controls than your car has. 1 lever for swing on the left, 2 levers on the right, 2 levers on the right for drag and hoist brakes, 2 foot pedals for drag and hoist brakes. That's the entire interface for a 180-foot boom and a 12 cubic yard bucket. And no matter how modern the cab gets, the work at the bucket end still looks the same. An excavator breaks apart rock at a waterline, muscle at the front, hydraulic pressure at the back, operator making 1,000 small decisions per hour. The machines got bigger and smarter. The problem they're solving hasn't changed since the first steam shovel bit into the earth. So here's the honest picture. The biggest excavators on the planet push engineering to its limits, but every one of them lives or dies by the mine around it. Cut the power grid, park the haul trucks, or stall the crusher, and even a 14,000-ton machine goes quiet. The bucket at the front gets the applause. The system behind it does the actual work. Every record-breaking machine is really a test of how reliable everything around it can be, which raises a real question worth thinking about. As mines push toward electrification and remote operation, will future operators control these machines or simply supervise them? Drop your take in the comments. Curious what the crowd thinks. Thanks for hanging with us all the way through. If you got something new out of this one, hit subscribe. Bigger machines are coming next. Take care.